Oh, wait.
So, hey everybody, welcome back to Big Calculus. So this is, it's been a couple days now since we talked about converting coordinates, but are these all look okay to you? The first one you can do maybe just by inspection, right? I mean, you really don't have to maybe even use the formulas. Yeah? It's 2 units that way, right? is all you have to say, right? Done. You know, so feel free not to use the formulas and to use intuition and basic common sense, right? On B, you kind of like, there's no shortcut really, you know, except you might recognize the Pythagorean triple, right? And maybe you know right away that R is 5, right? Finding theta is not fun though. It's in the third quadrant, so let's see, I want to know what Andrew did here. He did tangent, okay, I like tan inverse, and then you had to do what, Andrew? Yeah, and then add 1/8. So that's exactly what I would do too. I'd probably, for anything in the third quadrant, I'd probably take the inverse tangent of y over x, and then I'd add pi, or add 180. I didn't say whether to do degrees or radians, so this is fine. Okay, I assume this is right, by the way. Is it? Okay, I don't know. I didn't check, but that feels right. I mean, he did it right, obviously, but yeah, Holly.
Can I do like -5 and 36?
Sure. Oh, that's creative. A creative solution too. You could just say whatever the first quadrant angle is, and then use a negative r value. Absolutely, sure. And for C, yeah, that's in case that's hard to read. That's s times √2. Okay, and again, actually, you might know that, right? Maybe you know that, like, if this is like a 45, 45, 90 triangle. If you're thinking about it that way, you know, it's the first thing that comes to my mind. So I know that, like, if you have a triangle that has 45, 45, 90 triangle has legs 10 and 10, and the hypotenuse is 10 √2. You know that too for geometry, maybe. So again, maybe even. But if you do the formula, of course, it comes out to be s times the square root of 2 as well. And then again, 3 pi over 4, you can do the tan inverse. You'll get -1. You need to know that it's in the second quadrant. Or is it? I mean, actually, what quadrant is this coordinate in? I mean, it seems like it's in the second, but it could be in the fourth if s happened to be a negative number, right? Would this still be right then? Actually, yeah, right? Since if s is negative, then this does put us in the fourth quadrant. So actually, this is cool. This is right no matter how you slice it. Yeah. So it looks like she took the tan inverse of theta, tan inverse of -1, right? Because that's y over x. S over negative s is -1. She's sitting right next to you. You can ask her. And then of course that's not enough information. You still have to think about quadrants and stuff, right? But anything else you want to say about this formula? Okay. What about the homework? How are you feeling about the homework? It was fun. It was not too bad, I hope. I don't know. You did some of this. You also converted coordinates the other way, which I think is easier. Going the other way is a little easier. And you got to graph a few little equations too. You're just plotting some points, and right now not with very much thought necessarily, but you're beginning to see how you might think about plotting a function too in polar coordinates. Right? Just plug and chug. Did I see a hand somewhere? Thought I. You good?
For the
Yeah, go ahead.
the table on 6, like if you like it was like r equals 2 cosecant theta.
Okay.
And like if
You get some undefined things. Right?
Yeah.
Mm-hmm.
But if you convert it, it's like y equals 2. So what?
Yeah. So that's a horizontal line.
Right. So why are some of the
Yeah, that's a good question. So why do you sometimes get undefined values, right?
Yeah.
So for that particular one, you said it's r equals, what was it, 2?
2
Secant? Cosecant, excuse me. Cosecant theta, right? And you said it comes out to be this kind of picture eventually, right?
Yeah.
Right, it's y equals 2. Cool. So as you sweep around, the question is, you can think of polar coordinates as answering the following question. If theta is 0, that is if you take a ray from the pole out in the 0 degree direction, where does that ray hit the curve of interest? And the answer is, doesn't, right? All right, now as soon as we peek up just even a little bit, you know, like what's the answer? What if theta is 1 degree, do we get an answer?
Yeah.
And what do you think the answer is?
It's not really
Huge, right? Like when theta is 1 degree, r is, you know, actually we should figure it out, right? R is going to be like 1,000,000 or something, right? So, because that answers the question where, okay, you see how this is happening? So that's how I want you to think of polar coordinates, as like a ray sweeping out from the origin, sweeping this way, like boop, 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 you know, like looking at the display in the traffic control thing, right? The other place where it will have that happen is over here, right? Over here, this is a little weird, but because now we don't want to think about a ray anymore, right? We also want to think about maybe a line going in both directions. Because what about this? You might think, well, a ray coming out of the origin doesn't hit that, doesn't hit down here, but it does hit negative. And if you did this problem in homework, then you know that you're getting negative values there. It should make sense. You still are producing values on this line. So that's cool. And if you haven't tried it yet, you're welcome to play around with your calculator too. I'm gonna ask you to put your calculator into polar mode today and play around a little bit too. So we can have our calculator nearby. That's not the focus of today, but we can start at least acquainting you with that. Yeah, Sunil?
So like, if you like write that as like r equals 2 over sine theta, and
Yeah,
then
yeah.
like solve this as r sine theta
Mm-hmm.
equals 2.
Absolutely.
So then that's like y equals 2.
Absolutely, right,
But like,
right.
if it was like 2 like sine theta, or like r.
Then we don't know what to do, right?
Okay.
That's an excellent question, and that's what we're going to look at today, is how to convert equations back and forth. Because you're right. I mean, your hunch should be, as we move into today, your hunch should be, you're thinking, well, why do we even use polar if we can just, isn't y equals 2 easier? In that case, I think you're right. You know, y equals 2 is easier. But there are going to be some curves we're going to encounter where polar form is nicer, or it's impossible, really, to get a nice form in rectangular coordinates, okay? That happens to be one that's decent in both coordinates, but we're going to encounter a lot of really pretty pictures today. So today I want to, this is still in the same section. In fact, I probably could fit this all into one lesson, but you figure it's good to kind of relax our way into this a little bit. We're going to be converting not just points back and forth, but equations back and forth from polar to rectangular, or from rectangular to polar. And we're going to use the exact same tool belt that we used on Monday when we first were doing coordinate conversion, right? So remember these facts, please. Bring them back to mind. They're already in your notes somewhere. But they're going to be the same exact tools like Sunil and I were just talking about, right? That we're going to use to convert that equation that we were just talking about to y equals 2, right? That was an easy one. So, and in fact, actually, maybe you've already, maybe that's done then, right? So what is that one? Okay. So we've already had this discussion. All right. So yeah, it comes out to be so if you missed the discussion we were just having in the warm-up, let's have it now here. R sine theta. We're going to try and do some algebraic manipulations to produce these three situations, right? And there it is, R sine theta. Yay! All right, so the work here is done, and that's like the very simplest example that we could possibly give you, and the rest will be more complicated. But let's take this brief, simple opportunity to show you polar coordinates on your calculator. Okay, so I'd like you to go on your calculator and go to your mode menu, right? And then select polar. And then you should see, instead of in your y equals, you should see R1, R2, R3, right? Because we're thinking about functions R of theta. You can just do zoom standard right now. It's fine. And you should produce this picture. If you want to produce it more slowly or something like that, that'd be fine. You know, and you can trace this graph too and see what you see. What is it? 3 divided by sine theta. I'll do it again here. Right now, if you go to window, you'll see you get some new options here, right? Not just x min, x max, all that. But you also have theta control over the theta value, right? So right now it looks like theta is going from 0 to 6.28, right? You actually You actually don't need 0 to 2 pi, though, do you, for this picture? You could actually just do it with 0 to pi, and you'd still produce that line, right? Because you know, from your experience last night even, right, plotting a line like this, that as you come around to pi, you've created the line, and as you go from pi to 2 pi, you're hitting the line again, right? So you get this picture even if you just did 0 to pi. Try it. You feel free. If you want to do it more slowly, you can make your theta step smaller. Like, how about, yeah, it would be more accurate too, but whatever. How about pi over 48 or something? Okay. And I'd also like to, yeah, that's fine. We'll do that. Here, let's also turn that ball thing on. That'd be fun. There it is, okay. And notice how slow it is down here and how fast it is out here. Can you think about why that happens? I mean, we're already thinking about like rates of change, kind of, right? As theta changes a little bit down here, that means a lot, right? If theta changes a little bit here, close to the origin, you know, like around the top bend, you know, it doesn't actually move the coordinate very far, right? But that's an interesting discussion to start having. And if you trace this right now, you have x and y's, but if you want, you can also go to second zoom to the format menu, which maybe you've never used in your life. And instead of rectangular grid coordinates, turn on polar grid coordinates. And now when you trace left and right, it corresponds to theta increasing, and left corresponds to theta decreasing, right? So I know that's a little counterintuitive because you're going to hit right, and the cursor is going to go left, okay? So, see how that's working? So there we're at 1.57 radians, right? Which is pi over 2 radians. Maybe it's more intuitive for your sake if you were in degrees here. Oh, except now we have to do, okay, forget that. Yeah. It's all good. We'll just stick the way we had it. Anyway, you play around with polar on your calculator, and you'll get some nice pictures of these things. Okay. So why don't we try another one on your calculator? This is the one, in fact, someone asked about. What about 4 cosine theta, right? That's maybe not a line. So what is it, right? See if we can figure it out. Graph it on your calculator and make a guess. What do you think? Or maybe you can do without it. And maybe you can even guess what it's for. We'll prove it in a minute. Remember, if you're having trouble, you might be benefited trying to figure out what this is by using zoom square. I mean, once you establish a window, zoom standard or something, and then hit zoom square. And what that does is creates, your calculator is disproportionate, right? So it'll square up the coordinates. So the even number of pixels is equal to an even number of pixels on each axis. In which case, and you see why I'm saying that, right? Because then you realize this is what? Yeah, it's not an ellipse. It's actually a circle, right? It looks like an ellipse, and so like I said, so maybe zoom square to make sure you're convinced that it is in fact a circle. So I mean, you're right. Actually, it is an ellipse. Special case of it. Yeah, you get this picture. I zoomed in a little bit on it. Okay. So I think we're convinced that it's a circle. Maybe. Maybe you can even tell me, because of your prior knowledge with circles, what its equation is in rectangular coordinates. What would it be? It's got a radius of 2, it looks like, if you graph it carefully. Yeah, you're going to have to do like x minus 2, all that. Let's see what we get. Okay. So here's a trick that we'd like to use here. I'd like to go out of my way to produce the situations that we had in those 3 equations on the first slide, right? So I don't have that right now. But what if I were to take both sides of this equation? How could I produce, instead of a cosine theta? We don't really like cosine theta, but we do like r cosine theta. So what might we do on both sides of this equation? Maybe multiply both sides by r to produce an r cosine theta here. That'll produce an r squared over here, which actually is also convenient, isn't it? R squared is equal to x squared plus y squared. And this over here is for x now. And actually, we're done. right? So this would be a fine answer. Yay. We multiplied both sides by r and then made a realization that, I mean, this is part of the reason we did that, by the way, right? That we now have things that we know from the previous slide, that r squared is x squared plus y squared, and r cosine theta is just x. Yeah, cool, right? Would you like to see that in a little more canonical form? Maybe you would. So let's keep going, just for fun. This is fine answer, though. If it says convert to rectangular coordinates, we have done it, right? There is no r, no theta in our equation. That's beautiful. It's wonderful. But I think maybe you prefer to see it this way. Or adding 4. Complete the square. Have you done this before? Right? Complete the square, you know. All right. So now it's more obvious that, yes, in fact, we're right. This is a circle with radius 2, centered at 2, 0. Yeah, okay, cool. All is right in the world. So do you need to do this? No, not necessarily, but you might if you want to convince yourself of what this is and what it really looks like and all that. Okay. Can we go the other way? Here I've given you, what is this again then? This is a circle again. Looks like it's centered at -4, positive 3, with a radius of 5. Good. So can we go the other way? Well, yeah, it's not. Converting from rectangular to polar is not very interesting. We'll do it. We'll do it. But it's the other way around that's more interesting. So we'll just do one of these today, show you that you can go both ways. Yeah, well, let's multiply it out, but you know, you could actually not do that too, but let's multiply it out just to see what's going on. And something really convenient happens here that I think you'll like. Okay, I've crafted this one very, very specifically so that something nice happens. Is that -6x plus 9? And oh, sorry. And what do you what happens then? See anything fun? Yeah, it just so happens I picked the right numbers here. The 16 and 9 and 25 go away, right? So we get x squared plus y squared plus 8x minus 6y equals 0. Okay, interesting. Now I wrote that in a specific order because x squared plus y squared is r squared. This should feel like the previous problem, just kind of in reverse here. X is, can we replace x? And this is what I was saying. Is actually you could actually do this right away at step 1 if you wanted. X is r cosine theta, and y is r sine theta. And actually, again, we're done here, but maybe we can clean this up a little bit. You know, your inclination might be to divide through by r, for instance. And actually, that's not necessarily a legal thing to do, but r equals 0 is already a solution of the following equation, too. So I think we're okay getting rid of it. This so happens to be the case. Which means in this particular case, this is not always going to be true. But in this particular case, we can actually solve this for r, right? And that's good. I mean, really, like I said, we could have been done earlier if we wanted. But I think that's a nice way to write this. That's a function r of theta. That allows you, that's in a form that you could now enter in your calculator even, right? And see this picture. Okay. But again, we're using only those same tricks, right? X is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared equals r squared. Those are like our only tricks in the book, okay? But those are the only ones we're using, along with some tricky some algebraic fun things along the way too, trying to make this happen. So feel free to graph this on your calculator. You will see a picture of a circle centered at -4 through 3 with a radius of 5. It goes through the origin, happens to be, right? If you wanted to write this as one function of cosine, could you? Like with something times cosine of x minus something, maybe? Do you remember doing that? You could if you wanted. Yeah, let's not. But do you remember doing that though? linear combinations of sine and cosine. You can write as one function in terms of cosine. So you can play around with these even more if you wanted. Speaking of things that you've forgotten, let's do this one. Okay? You're not going to like this one. Okay? You're not going to like this very much. I'm just going to say that now. Our three tricks, right, are cool. They're wonderful. We've been using them well, but they require that we see cosines of theta and sines of theta. We like cosines of theta and sines of theta, but we do not really like cosines of 3 theta. Yeah. So what can we do? Well, maybe we can put this in terms of sines and cosines of just theta. And this is the part you're not going to like. You do know how to do this. All right, so here we go. We're going to fill the slide with some fun trig. Here we go. So can we rewrite cosine of 3 theta in terms of, oh, I don't know, cosines and sines of 2 theta and theta? Yeah, we can. What do we get? Cosine of 2 theta plus theta. What is the cosine sum formula? This is the part. Yeah, I should give someone a. All right, candy for the person who can name the cosine sum. You got it? Go ahead.
Cosine squared theta minus sine.
Close. No.
Is it sine, cosine, plus cosine,
Sine, cosine plus cosine, sine. Close.
Oh, wait, no, wait. Sine, cosine, cosine.
No. Close. Who wants it? Maybe.
Cosine theta, sine theta, minus sine theta, cosine theta.
Oh, yeah.
Yeah. Yes.
Theta's everywhere. Say it one more time.
Cosine theta, sine theta, minus sine theta, cosine theta.
Okay, let's say it this way. What is the sine? What is the cosine of a plus b? What is it?
Cosine A sine B minus sine A cosine B.
No. That's why I had to ask. Okay, close. Lizzie's got it though.
Cosine A cosine B minus sine A sine B.
No. Jack, maybe?
Is it cosine A, sine B, cosine B?
A lot of good guesses here. Actually, I'll return to Varsha's here. Remember, I know the double angle. This is my thought. I know the double angle is cosine squared minus sine squared. If A and B are the same thing, right? So it's got to be cosine, cosine, sine, sine. Okay. And then what's the sign in the middle? No one gets the. Yeah, it's cosine A, cosine B, minus sine A, sine B, right? I have to think about it too, though. It's been a while, right? All right, now we're ready. What do we get? Cosine 2 theta, cosine theta, minus sine 2 theta, sine theta. All right. And then cosine double angle and sine double angle on. Now we need yours, Varsha. All right, so cosine double angle. We just did that. Just right. It'll be cosine squared minus sine squared. And sine 2 theta, what's that one? It's a nice one. I made you think about that. Yeah, I made you think about that one recently on something or other, on a warm-up or something. Okay. Yikes. All right, let's play around with the stuff inside there. We got cosine cubed. Okay, all right. Minus a sine squared cosine. Sine squared cosine. Okay, so there are actually 2 of those. I'll write it out, but we'll be able to combine these. That'll be fun. Are we having fun yet? Yeah, maybe we should know the sum and difference formulas and the double angle formulas again. That'd be good to memorize those again. All right, if you want to multiply the 6 through, we could do that too, whatever. Now we're in good shape here. All right, but what was our goal? Rectangular coordinates. Okay, we're still not seeing any x's and y's yet. Okay, so we have the one goal accomplished though. Write everything in terms of cosines and sines of theta and not 3 theta. Good. Now, again, actually, we're not a fan of cosine theta still. We actually want to go further. We would like to see an r cosine theta. Or here, we'd like to see r cosine theta all cubed, right? So actually, we need like an r cubed out here, don't we, on this first guy, in order to like make ourselves happy. We'd like, for every cosine theta, for every copy of cosine theta, we need a copy of r. We could take out a cosine if you want. Sure. Yeah. What about over here? We need an r for this sine theta. Oh, another r for this sine theta, and an r for this cosine theta. So it looks like I need an r cubed. Is that okay with you? I'm going to multiply through by r cubed everywhere. Right? That gives me an r to the 4th over here. It'll give me 6 r cubed cosine cubed theta minus 18 r cubed sine squared theta cosine theta. And I'm going to rearrange some things here. This is r squared squared. This is 6r cosine theta cubed. This is r sine theta squared times r cosine theta. And let's stop there for a second. Is everyone okay with those? You can. I hope you see why I'm doing what I'm doing, right? Because this is the big move at the end here. Good. Stare at it for a minute. Make sure you get it here. Okay, so are you okay on this step here, Janetta? I'm multiplied through by r cubed. Okay, and then here I'm just making some rearrangements. And whether you understand why I'm doing it or not, do you understand that I can do it? Like here, isn't this the same as this?
Yeah, I get the
Okay,
first part.
but this, so I'm taking an r squared, so this will be r squared sine theta, sine squared, right? But wait, where's the r cubed? Well, I put another r over here. Is that okay? I mean, I just rearranged it. Multiplication is associative and commutative. I can move that r, those 3 r's, wherever I need them to be in the product. Yeah. Yeah, so why am I multiplying by r cubed? If it's not made obvious yet, it will be right now, right? So what do we have here? Over here we have x squared plus y squared squared. This is x cubed minus 18 y squared x, and we've done it. Okay? Now, the bigger question that you might have in your mind too is, well, what have we done? What is that? You know? We have done it. It is in rectangular form. Please don't make me solve that for y, though, okay? Because I'm not going to do it for you, okay? Because it looks like this. Feel free to graph this in polar coordinates. Graphing this in rectangular coordinates is possible, but this is an implicit curve, right? Here where we studied briefly implicit curves last semester, right? We can't really solve this for y very nicely. We could actually, and it would be like we could break it into a whole bunch of pieces or something. But this is an example of one that in polar coordinates is elegant and beautiful and simple and conceptually nice, but in rectangular coordinates is possible but not necessarily fun, right? So feel free to graph that on your calculator, and eventually we're going to start analyzing this. I'd like you to be able to graph these later, but we'll save that for another day. But it is fun to start at least playing around with these. Yeah, we're going to, like I said, we're going to produce some pretty pictures. This is, you might call this a flower or something. You could think, how could I get more petals on my flower? And you can start playing around with that. It'd be fun. And then if you haven't yet, fellows, if you haven't yet, you know, found that special someone to take to prom, you could like, this could be your, you could produce a polar bouquet.
Is that how you ask her for prom?
I'm just saying. And Mother's Day is coming up. She might like a polar flower. Polar flower? Okay, I'm just saying. Okay. Yeah, that's the way to bring the calculator out. That's what warms the heart. Okay. All right, and then one last thing I should say before we are convinced that everything is beautiful. This is a wonderful curve in polar coordinates, But I just want to say that there's really nothing we can do to make this nice and rectangular coordinate. So I will show you our best ditch effort, but you'll see it's wrong and not good. You know, so this is our best ditch effort. There are no cosine. In fact, thetas are not nice. We don't really like theta. We love cosine of theta and we love sines of theta. Those are cool. We've seen that today, how nice those can be. But here we don't have any real great recourse. So what could we write? Well, I mean, we could write this. But that's a little bit of a lie because r is sometimes negative, and here, right? And over here we could write tan inverse of y over x squared, you know, but that's a lie. Lies, okay? Okay? But that's the best we could do if we wanted to try, right? And the reason is because it looks like what? Did anyone graph this? Looks like that. It's a spiral. This is cool, right? So feel free to grab it. So there are all sorts of things that are possible. So sometimes it's possible, like we just saw, even though it's painful to convert to rectangular coordinates on the last slide. But here, it's not really that possible, but you do have still something that's pretty beautiful in polar coordinates, right? Homework 2 tonight, yeah.
Is that like the last one?